Okay, it's my pleasure to introduce Kaloyan Slavov, who will talk about the modular space of hypersurfaces whose singular locus has high dimension.
Thank you. Thank you very much, Antoni. The goal for today is to illustrate once again the technique of proving a statement over an arbitrary algebraically closed field by reducing to point counting over finite fields. Now, let K be any algebraically closed field. On Monday, we looked at the moduli space of hyperplanes. Now we're going to look at the moduli space of hypersurfaces of fixed degree. Consider the following X defined as follows. All hypersurfaces, so I'll think of polynomials in P, K of x0, xn, homogeneous degree L. So this projective space, this is the projective space of hypersurfaces of degree L, such that dimension of V of f singular locus greater than or equal to 1. Hypersurfaces singular along some unspecified curve. You can look at this X and ask what is the dimension of X? What is the dimension of X? And what is an irreducible component of largest dimension? This is the question that we'll be looking at. Now, there is a candidate for this. So you have to build a family of hypersurfaces, each member having a singular locus of dimension at least 1. And there is a candidate, namely x1, consisting of O, F. Let's call this vector space V. So in P of V, in the same projective space, such that V of F singular contains an unspecified line. It's easy to check that this is an irreducible closed subset of X. You set up an incidence correspondence between line and the hypersurface so that the line is contained in the singular locus of the hypersurface with dimension of x1. It's easy to calculate the dimension of x1. It's the dimension of Grassmannian of lines plus the dimension of the space of hypersurfaces singular along a given line. And what you get is L plus n choose n minus the quantity I'll call A of L, where A of L is equal to NL plus 4 minus 2n. That's a very easy calculation, irreducible closed subset of this dimension. And this is our candidate. This is our candidate for the irreducible component of X of largest dimension. Indeed, theorem. That's what I managed to prove with an assumption that L is large. At least for sufficiently large L, this is the case. There exists an L0, which depends on n and also on the characteristic of the field, such that for all L greater than or equal to L0, remember L is the degree of the hypersurfaces that we're considering. For all such L, x1 is the unique irreducible component of X of maximal dimension. Also, I should say, we also have a statement where instead of dimension singular locus greater than or equal to 1, we can say dimension of the singular locus greater than or equal to any positive integer that you like. And then you have to look at hypersurfaces containing a linear subspace of that dimension. And also we have a statement about the second largest component. It will come not from lines, but from plane quadrics. But I will focus on that for expository purposes. In fact, also for expository purposes, let's say that n is equal to 3. This case avoids some technical complications and again illustrates already all the ideas. Now, the reason this is difficult, what makes this problem difficult, is that if I give you a single curve of large degree, it will be difficult for a hypersurface to be singular along that curve if the curve has large degree. There will be fewer such hypersurfaces compared to hypersurfaces singular along a line. But curves of large degree come in larger dimensional families. There are more of them. The curves of large degree come together in families of large dimension. That's the problem. And what happens when you increase the degree of your family of curves where your hypersurface will be singular along? Well, it will be difficult to be singular along a specific one, but there are too many of them. And that interaction makes it difficult. Okay, now the first half of the talk will assume some scheme theory, and the second half of the talk will be point counting over finite fields. That's the plan for today. Now we start by parameterizing. So let's say for d greater than or equal to 1, we'll be parameterizing families of curves. Here my condition is that the dimension of the singular locus is at least 1. That is to say, the singular locus contains some curve. What curve? What kind of a curve? For d greater than or equal to 1, there exists a finite set. Let's call them PD alpha of polynomials in Q of z with rational coefficients, such that for any k algebraically closed field and for any c inside Pn over k integral curve of degree d, the Hilbert polynomial of C is in the collection PD alpha. That is to say, there are finitely many Hilbert polynomials of integral curves of degree d over the various algebraically closed fields. And the reason for this is the Hilbert polynomial is determined by the degree and the arithmetic genus, and you can bound the arithmetic genus in terms of the degree. So these are our finitely many possible Hilbert polynomials of all integral curves of degree d. Now let's define the Hilbert scheme Hilb d to be the disjoint union of the Hilbert schemes Hilb P3 with respect to the polynomial PD alpha, disjoint union over alpha. We put all of them together with respect to the corresponding polynomials. So this Hilbert scheme Hilb D parameterizes subschemes with a Hilbert polynomial among the collection P alpha D. Now, let's set up an incidence correspondence. So let's consider all pairs C and F inside Hilb D. So C will be an integral curve. Let's call it not an integral curve. It will be a closed subscheme with Hilbert polynomial, one of these, and F will be a hypersurface, such that C is contained in V of F singular locus. A curve and a hypersurface, so that the curve is contained scheme theoretically in the singular locus of the hypersurface. We set up this incidence correspondence. Now, it comes with two projections. Pi is the projection to the Hilbert scheme, Hilb D, and rho is the projection to the space of hypersurfaces. Now, when d is small, well, let's see what we'll do. We'll give two separate arguments, when d is small and when d is large. And the talk will focus on the case when d is large, but I also sketch what happens when d is small. You'd love to give an upper bound on the dimension of this incidence correspondence. Let's call it omega d. If you give an upper bound on the dimension, that would be great, because then you project this by the second projection rho, and then you get the set of hypersurfaces singular along something in Hilb D. However, the Hilbert scheme can have a very large dimension. It doesn't behave well. The Hilbert scheme can have components of really big dimension coming from families with general member really non-reduced. So this can have very large dimension. That's the problem. However, we don't need the full Hilbert scheme. We can work with Hilb tilde D. There's a risky closure in Hilb D of the set of points corresponding to integral curves. I can look at families whose general member is an integral curve. And that dimension is tame, that is controlled. So here let's put tildes in our incidence correspondence. We put tildes. And now we can bound this dimension. So this has a reasonable dimension. This has a small dimension, at least when D is small. Now, let me just write down another thing that I mentioned. Why do we set this up? Our X, everything so that all hypersurfaces so that the singular locus contains some curve is X1, those that contain a line, union rho of, let's call this omega tilde. Actually, I added a tilde. Omega tilde 2. Union. What is rho of omega tilde 2, the image under the second projection? These are all hypersurfaces whose singular locus contains a curve, a one-dimensional subscheme in Hilb tilde 2. And so on, and so on. Rho of omega tilde n, actually, where n is L minus 1 to the fourth. Now, our singular locus, V of f singular, this is the vanishing of f and df dxi, the partial derivatives. So it's determined by the vanishing of something of degree L and 4 partial derivatives of degree L minus 1. And this capital N, by Bézout's theorem, is a bound on the sum of the degrees of all the irreducible components. And if V of f singular locus has dimension at least 1, it will have at least one irreducible component of dimension at least 1, and the degree of that will be at most capital N. And if you slice it with hyperplanes if necessary, then you will get a curve in the singular locus of degree at most this capital N. So it's really a finite union like that. And our goal, it would be great if we bound these dimensions. Yes, it would be great to bound these dimensions. And then that's why we're interested in bounding the dimensions of the incidence correspondences. Now, let's see what happens here. How do we give a bound? We look at the first projection, pi. Theorem by Eisenbach-Harris. (1992). They give, we don't really need this theorem, by the way, but the proof becomes more explicit if we actually use it. They give a bound for this restricted Hilbert scheme, they call it, Hilb tilde D. Namely, dimension of Hilb tilde D, Hilb D tilde, is equal. What is the largest dimension of a family of curves of degree D in P3? Let me emphasize here, this is in P3. Of a family of, yes, of a family whose general member is an integral curve. Well, it turns out the largest dimensional family is the one corresponding to plane curves of degree D. So the bound is 3, being the dimension of the Grassmannian of planes, plus D times D plus 3 over 2. This is the dimension of the space of curves of degree D in a given plane. Okay, so we have a bound on the dimension of the Hilbert scheme. So coming back here, this is controlled. This dimension is controlled. And now, how do I give a bound on the incidence correspondence? I have to take here an integral curve and bound the dimension of the fiber. So for an integral curve C, for C in P3, integral curve of degree D, give a bound, upper bound, for dimension pi inverse of C. Pi inverse of C is the space of hypersurfaces whose singular locus contains specifically the curve C. And here's the thing, it's possible to do it. It's possible to give a bound. We'll think geometrically. Here's how you do it. Let's say this is your curve. Here it should be like this. This is your curve, and this is the vanishing of x3. Without loss of generality, the curve C intersects transversely the hyperplane V of x3. So it intersects it in D distinct points, like that. And now we can degenerate the curve to a union of lines. We can apply a degeneration technique. So with the projective linear transformation AA, which has A on the diagonal and then 1 at the bottom right, A not equal to 0. And you can take CA to be this transformation applied to C. So we start with the curve and then we apply these linear transformations. Now, CA is projectively equivalent to C. It's projectively equivalent to C. And the CAs form a flat family over A1 minus the origin, because A is non-zero and we have this flat family over A1 minus the origin. When you have a flat family over A1 minus the origin, you can take a flat limit. We can take a flat limit and you can take limit as A goes to 0 of CA. This is the flat limit. What do you get as the flat limit? Well, here if I take the point 0, 0, 0, 1, it turns out for the flat limit, you get topologically a union of lines is equal to L1 union LD. Oops. Set theoretically, topologically. Scheme theoretically, it may not be with the reduced structure, but set theoretically, you get this. This is a degeneration technique. Let me perhaps give an example. E.g., let's say you take y equals x squared plus x, your favorite parabola. Here is -1, here is 1. And I can take ay equals x squared plus x for all a not equal to 0. This is a parabola that looks more like this. More like this. And then, so I get a family, a flat family of degree 2 curves, C0. And then C0 in this case will be x squared plus x equals 0. So the initial parabola degenerates to the union of two lines, x equals -1 and x equals 0, passing through the point at infinity. So you can degenerate the curve to a union of lines. And now let's go back here to what we're doing. We're looking at this projection pi, yes? The projection pi. We have a bound on the target, the Hilbert scheme. But by the way, this method is only good when D is small, because you can see when D is large, the dimension of even the restricted Hilbert scheme, it will keep growing. Now, when D is small, we have this good bound on Hilbert tilde D, and we're bounding the dimension of fibers. But we have this flat limit. The flat limit is a special point. Every neighborhood of the flat limit will contain some point CA, some curve CA. We think of the curves CA as points in this Hilbert scheme. So here is the original C, and then there are the different CAs, and then there is the flat limit C0. But any open neighborhood around C0 will contain one of the CAs, but CA is projectively equivalent to C. So the upper semi-continuity theorem, upper semi-continuity implies the dimension of pi inverse c less than or equal to dimension of pi inverse c0, because at a special point the dimension of the fiber can only go up, it cannot go down. C0 is a special point. Any neighborhood of C0 contains a curve projectively equivalent to C. Now C0, the flat limit, may not be reduced, but if you reduce it, you get dimension pi inverse of, here is C0 with the reduced structure, which is the union of lines, Ly, I from 1 to D. And this thing is easy to bound. Easy to bound. You have to bound the space of hypersurfaces singular along each of these lines. And that's a very explicit calculation. I will skip it, but that's very easy to bound. Okay, and then all we have to do is we check that the dimension of the Hilbert scheme, we only need the restricted Hilbert scheme. The reason we're working with the restricted Hilbert scheme is that if a hypersurface contains a curve in its singular locus, it also contains an integral curve. So for us, families of integral curves are good enough. Plus dimension of the fiber, we explained how to bound the dimension of the fiber. We check this is less than the dimension of x1. And therefore, this incidence correspondence that we had above, here, dimension Hilbert scheme plus the dimension of fiber less than the dimension of the incidence correspondence, and also therefore the image of the incidence correspondence under rho is less than dimension of x1. Now this holds for L greater than or equal to 6, and most importantly for small values of D, 2 less than or equal to D less than or equal to L plus 1 over 2. Only for small values of D. For large values of D, again, you cannot do it because the Hilbert scheme has dimension that keeps growing. Okay, now we move to the case of large degree. We have to give a completely different argument when D is large. We are looking again at the incidence correspondence, but now we define a universal incidence correspondence. Incidence correspondence. Now, what we're doing is we are parameterizing our hypersurfaces with singular locus of dimension at least 1. Namely, we can define an incidence correspondence inside Hilb D, the Hilbert scheme. Now, no longer the restricted Hilbert scheme, because I'm taking it P3Z here, the Hilbert scheme over Z, and then times the projective space P of Z of x0 until x3 homogeneous degree L. Not working over the algebraically closed field K, but working over Z. You can still define an incidence correspondence. It parameterizes pairs of a subscheme, that is to say, something that the Hilbert scheme parameterizes, subscheme, comma, hypersurface, so that the subscheme is contained in the singular locus of the hypersurface. You define it, the way to do it is you define it as a functor, and then you prove that this functor is representable by a closed subscheme. You know what it should be on the level of K points, what we wrote before, but you have to define it for all S points. Now this maps down to the projective space P of Z of x0, x3, homogeneous degree L. This is a projective space over spec Z. And I can look at the scheme theoretic image, because this from omega D to this projective space, all arrows here are projective morphisms. So the scheme theoretic image, TD, is like this. I have a surjection followed by a closed embedding. And the TD is what we're really interested in. This TD is our moduli space. What is the TD? For every K algebraically closed field, what is TDK? TD, if I base change to K, now it is closed inside our P of K x0, x3, homogeneous degree L. It's a closed subvariety, closed subscheme inside our projective space of hypersurfaces of degree L. And it parameterizes, look, it's the image of the incidence correspondence to the space of hypersurfaces. Parameterizes hypersurfaces singular along something, some point in the Hilbert scheme. So it is OF, O hypersurfaces, such that the singular locus, V of F singular, contains, it should be in the image, so contains a closed subscheme of Hilbert polynomial, among the polynomials P alpha D. That's technically what it is. You should be thinking as it parameterizes hypersurfaces singular along a curve of degree D. Let's call it this way, a curve of degree D. But it may not be a hypersurface, a point in this TD may not be singular along an integral curve of degree D. It may be singular maybe along a line, but this line has some fancy scheme structure so that it's actually, with its scheme structure, it has degree 2 or 3. So this is the TDK. Now notice, our X is the union X1, those hypersurfaces singular along a line, union T2K, union TNK, where again n is L times L minus 1 to the fourth. That's because if the singular locus is at least one dimensional, it will contain, the singular locus will contain an integral curve of degree at most this capital N. Okay, so these are closed sets now. We split X as this union, and the goal is to prove that the dimension of TDK less than dimension of X1 for D greater than or equal to 2. Once we prove this, then X1 will pop out as the irreducible component of largest dimension. We write X as a union of closed subsets. X1 is one of them, and if we bound the dimensions of the others, we're done. And again, TD parameterizes hypersurfaces whose singular locus contains something of degree D with Hilbert polynomial and so on. Now, here is the thing. TD is projective. TD, look here, it's closed in this projective space, and this is over spec Z. So TD is a projective morphism. TD to spec Z is a projective morphism. TD is a projective scheme over spec Z. And therefore, we can again apply the upper semi-continuity theorem. We can compare the generic fiber with the special fiber of TD. Remember, that's what we were doing last time. We defined this universal moduli space embed, and then we were taking generic fiber versus special fiber. Here, again by upper semi-continuity, it follows that, let's say you're interested in the problem TD over the complex numbers maybe, or any other algebraically closed field of characteristic 0. Surely this is dimension TD over Q. By changing from one field to another doesn't change the dimension. But here is the thing. Here we use upper semi-continuity. Less than or equal to dimension TD over FP. This is a special fiber, and on the left we have the generic fiber. And this is surely equal to dimension TD over FP bar, where P is any prime. Okay, so if we have to give an upper bound on the dimension of TD, suffices to do it. So here, so we can assume K, our ground field, is FP bar. We are reduced now to positive characteristic. When you have to give an upper bound on the dimension, it suffices to do it when the ground field is FP bar. And then it will follow, the upper bound will also follow in characteristic 0. Okay, now, so now we reduce to positive characteristic, and next we'll reduce to point counting over finite fields. Assume case FP bar. For a technical reason, don't worry too much about it, but we have to actually define TD check. TD check, I will explain what it's doing. It's TD minus the union of the previous ones, minus TD prime. D prime is from 1 to D minus 1, where D greater than or equal to 2. We have to exclude the previous ones. Now, it parameterizes, this one parameterizes hypersurfaces whose singular locus contains an integral curve of degree D. If F belongs to TD check over K, yes, if it's in TD check, then its singular locus contains an integral curve, surely, because the singular locus has dimension at least 1, but it's in none of the previous TD primes, and therefore V of F singular contains an integral curve of degree D. That's what we want. That's why we take the check. Otherwise, something in TD, the singular locus may be a line with a very complicated scheme structure. But here we know it contains an integral curve of degree D. And remember, our goal is to give an upper bound on the dimension of TD. Proposition. There exists an L0, which depends on the characteristic P. We are now working, our ground field is FP bar. That's it. Forget about, never mind about characteristic 0 anymore. Such that whenever L is large, and whenever D is greater than or equal to L plus 1 over 2, remember the cases of small d we handled before by using the restricted Hilbert scheme and the argument at the beginning with the incidence correspondence. Now D is large, and for D large, dimension of TD hat over FP, TD hat exists over spec Z, base change to FP, less than dimension of X1. And this will imply dimension of TD over FP less than dimension of X1, and we'll complete the proof. It's a really small technicality going back and forth between TD and TD hat. TD hat is what we really should be working with. So the singular locus contains an integral curve of degree D, and TD is what really shows up in our decomposition of X. Okay, so now we have to give a bound on the dimension of TD hat over FP. Now let me emphasize, this is a variety over a finite field FP. And we have a technique, namely the Lang-Veil bound and point counting, with which we can give a bound on the dimension of a variety over a finite field. To prove dimension, so let's say Y is a variety over a finite field, let's say over FP. To prove dimension Y less than or equal to A is equivalent to proving that the number of FQ points on Y grows like big O of Q to the A as Q goes to infinity. If we prove this bound on the number of FQ points, this gives us a bound on the dimension. This is by the Lang-Veil. 1954, by the Lang-Veil theorem. If Y were to have dimension greater than A, if you extend the field appropriately, you will have Q to the A plus 1 points. Okay, so now we reduce to point counting, and let's look at an FQ point of T hat. If F is in TD check of FQ, by the definitions, when you unravel the definitions, then V of F singular locus contains an integral curve. That's why we were taking the check. So it's an integral curve of degree d over fp bar. V of f singular, considered, so if f is here, so f is essentially, f is a polynomial with coefficients in fq, non-zero polynomial with coefficients in fq of degree L up to scaling. Consider f with coefficients in fq bar, and then the fq singular locus, the vanishing of f along with its partials, contains an integral curve of degree d. This is the description of this set TD hat, TD check. Okay, so we have to give an upper bound on that. To give an upper bound on that, here's how we proceed. And that's the end of the scheme theory part of the talk. From here, we start the point counting over finite fields. What is left to do is give a large supply, of f polynomial with coefficients in fq, x0 until x3. We decided that n is equal to 3, homogeneous of degree L, such that v of f singular, if you consider f as a polynomial with coefficients in fq bar, the vanishing locus, the singular points in the vanishing locus, v of f singular, contains no integral curve of degree d, greater than or equal to L plus 1 over 2. That's all that we're left to do. I will scroll up. We don't need what we've been doing so far. This is what the problem is reduced to. We have to produce many f's, homogeneous polynomials with coefficients in fq of degree L, such that when you look at the singular locus, v of f singular, it contains no integral curve of large degree. And that's it. Now we have translated to a point counting problem, in this case, polynomial counting problem over finite fields. In the remaining 25 minutes, do we have 25 minutes, Antoni, roughly? Yes? Okay, in the remaining 25 minutes, we're going to do this. Okay, the technique, by the way, here let me emphasize, the condition we are imposing is geometric. F has coefficients in fq, but here we are considering this v of f singular locus. F, first you consider f with coefficients in fq bar, and then you take the singular locus. And then it contains no integral curve. That integral curve could be, again, over fq bar. So the condition is geometric, but f has coefficients in fq. Now, the technique is inspired from Bjorn Punen's Bertini theorems over finite fields. But I would say that this counting argument, this came up as a question last time, this counting argument that we'll see now really has nothing to do with the counting argument we were using in the first and second lecture, the random sampling. The only thing there is in common is that they're both counting arguments over finite fields, and there is the probability language. But the probability language is just convenient when you count stuff over finite fields. Other than that, the actual method is completely different. Okay, so inspired from this, here's what we do. Again, for expository purposes, let's consider L. Remember, L is, we're looking at hypersurfaces of degree L. Consider L congruent to 1 mod P. This will simplify some of the notation. Now, I will use the language of probabilities because it's convenient. We could avoid it if we want to, but we don't want to. It's convenient. As F in FQ, x0 until x3, homogeneous of degree L, is chosen uniformly at random, let E be the following event. Event that all of the following 3 items take place. Number 1, dimension of v of df dx0 is equal to 2. That's pretty easy to achieve as long as df dx0 is a non-zero polynomial. As long as this partial derivative is not identically zero, this vanishing locus will be two-dimensional. 2 dimension v of df dx0 df dx1 is equal to 1. If df dx0 and df dx1 were sort of generic, random, whatever word you want to use, that should be the case. Yes, that shouldn't be difficult to achieve. And 3, if C inside this vanishing locus, df dx0, df dx1, is an integral curve of large degree, greater than or equal to L plus 1, greater than or equal to L plus 1 over 2, then C is not contained in the vanishing of df dx2. Now, whenever this event E takes place, then V of F singular locus contains no curve, no integral curve of degree D greater than or equal to L plus 1 over 2. We want to exhibit a large supply of polynomials f so that V of F singular contains no integral curve of degree D greater than or equal to L plus 1 over 2. And whenever the event E takes place, that's it. There is no chance for an integral curve of large degree to be contained in the singular locus, just looking at 1, 2, and 3, the 3 bullet points. Okay, so our goal, remember, we had to prove that the dimensions of these TD moduli spaces were less than dimension of x1, and then we reduced to point counting, and then we reduced to giving some bound on the number of FQ points. When you restate it in the language of this, the goal is that we have to show that probability that E takes place greater than or equal to 1 minus 1 over Q to the A minus 1 for Q sufficiently large, where A is A of L is equal to 3L minus 2. When you work out the numerics, that's what we're reduced to. So here, again, from here, the rest of the talk is independent from the first part. That's what we're reduced to. We have to exhibit a large number of polynomials which satisfy 1, 2, and 3. Namely, we have to show probability of E is greater than that, and that will do it. That's equivalent to the inequality that we're shooting for. Now, here is what we do. Generate. The problem here is you have these partial derivatives, df dx0, df dx1, df dx2. They all depend on f. They all come from f. That's the problem. They're not like independent quantities. If instead of the 3 partial derivatives, instead of them you had completely separate polynomials, g0, g1, g2, then of course plenty of polynomials that I can put here will satisfy number 1, plenty of polynomials then I can put here satisfy 2, and plenty of polynomials will satisfy 3. But these partials, they're not independent. That's the problem. And the idea that Björn Poonen uses in his paper, and that we use right here, is the following. We generate a random f in fq x0 until x3, homogeneous degree L, by the following formula. F, write it as f0, a polynomial, plus a polynomial to the pth power times x0, plus a polynomial G3 to the pth power times x3, where f0 is in fq, x0 until x3, homogeneous of degree L, and gi is in fq, x0 until x3, homogeneous of degree L minus 1 divided by p. Let's call it tau. Tau is equal to L minus 1 divided by p. That's why we assumed L is congruent to 1 modulo p. Now, here's the thing. If you give me a random f, a random g0, a random g3, and then I form f, this is a way to produce a random polynomial f. To put it formally, the map which sends a tuple f0, g0 all the way until g3 to f by this formula has all fibers of the same size. So when it comes to probabilities, I can take the probability as f runs over the polynomials in fq, or I can take probability as f0 runs where it runs, g0 is where it is, and g3 is where it is. So now I can look at f0, g0, and so on. And why is this useful? Why is it useful to write it like this? Well, I will write it in red, because df dxi, if I take the partial, df dxi is df0 dxi, plus, if I take partial with respect to xi, notice what happens. I just get gi to the pth power. This is separating the partial derivatives. To make them almost like independent variables, almost as if they're independent variables. Okay, so now we're in a really good shape. Fix f0. Remember, f0 is the thing at the beginning. Now, what we're going to do is we fix f0. Once f0 is fixed, we're going to look at g0. We'll be choosing g0 and then g1 and then g2. Okay, fix any f0 where it should be in fq of x0 until x3, homogeneous degree L. Claim 1, as g0 is chosen uniformly at random in fq, here, degree tau, g0, remember when I look at g0, this will tell me f0 is fixed already, and if I look at g0, this will tell me df dx0, the first partial, and the first partial is what's involved in condition number 1. I want the vanishing of the first partial to be two-dimensional. That is, I want the partial df dx0 to be non-zero. The probability that 1 holds greater than or equal to 1 minus 1 over q to the tau choose 2, tau plus 2 choose 2. That's very easy to prove, because the only way one fails, i.e. df dx0 plus g0 to the p is equal to 0 for at most one value of g0. If you know that this is 0, there is at most one such value of g0. And therefore, the probability that 1 holds greater than or equal to the number of all polynomials, q to the tau plus 3 choose 3, the number of all choices for g0, minus 1 bad one, over q to the tau plus 3 choose 3, greater than or equal to 1 minus 1 over, and then the denominator, but I can give a bound tau plus 2 choose 2. Okay, I could write tau plus 3 choose 3, but let's just go with tau plus 2 choose 2. This claim is easy. 1 is very easy to achieve. There is at most one bad value of g0. Okay, now fix a g0 such that 1 holds. Fix a g0 so that 1 holds. Now we want to handle items 2 and 3. For item 2, here that other partial derivative comes into the game, and for item 3, that partial derivative enters the game. Now, I don't want the component of df dx0 to be contained in df dx1. So let's look at the probability for 2. Claim 1, claim 2. As G1 is chosen uniformly at random in FQ of x0 until x3, homogeneous of degree L, probability that 2 holds greater than or equal to 1 minus L minus 1 divided by Q to the tau plus 2, choose 2. We'll get to this bound, we'll prove it. Now let me just say equivalently, if it's more convenient to think equivalently, probability that 2 fails less than or equal to L minus 1 divided by Q to the tau plus 2, choose 2. We're going to prove it in the language of 2 failing, and then we'll be using it as written in the claim, probability that 2 holds. We'll be using lower bound for probability that 2 holds. Okay, how does 2 fail? Let's go back, remind ourselves what 2 is. 2 says that the vanishing of this variety is one-dimensional. If the 2 partials, if instead of, again, if these were 2 random generic polynomials that you plug in, you should get something one-dimensional. But here we have to be careful. They both depend on f. The f dx0 is already determined because g0 is already fixed, and the f dx0 depends only on f0 and g0. Now the f dx1. Okay, so here let z be an irreducible component of vanishing of df dx0. df dx0 is already decided because df dx0 depends only on f0 and g0 by the formula in red. f0 has been fixed. g0 is also fixed. We fixed the g0 so that one is satisfied. There are at most how many such irreducible components? Well, this has degree, this variety, the vanishing of df dx0 has degree at most L minus 1. F has degree L. So there are at most L minus 1 such z's. At most L minus 1 such components. And that's why we get this L minus 1 in the numerator when we write down the bound. Probability that 2 fails less than or equal to L minus 1 divided by this. L minus 1 being the number of possible irreducible components. Okay, fix such a z. So let z be an irreducible component. What remains to prove is claim the probability that z is contained in the vanishing of df dx1. That's what we don't want. We should bound this less than or equal to q to the minus tau plus 2, choose 2. If we prove this, we're done. We got the L minus 1 and then times the probability that the given irreducible component is contained in the vanishing of the other partial. Okay, now let's play with this. df dx1 was df0 dx1 plus g1 to the pth power. Yes, this is by the way we were splitting the partial derivatives. Okay, let I be the ideal of z. Z was an irreducible component, so I is a radical ideal. Now, now we're varying G1. G1 is running in homogeneous polynomials of this degree tau. G1 is chosen uniformly at random. Now, if df0 dx1 plus G1 to the p belongs to I, so if G1 is one of these bad choices for which number 2 fails, and if df0 dx1 plus G1 hat to the p belongs to I. So that is to say, if G1 and G1 check are bad choices for G1 to make this condition 2 fail, that is an irreducible component is contained in the vanishing of the partial derivative, well, therefore, G1 to the p minus G1 hat to the p belongs to I. But we're in positive characteristic. That's one advantage of positive characteristic. You can write like that. The difference to the pth power. I is a radical ideal. Therefore, G1 minus G1 hat belongs to I. And look here. The moment you pick a G1, which makes condition 2 to fail, then any other G1, namely any G1 hat that makes condition 2 fail, differs from G1 by an element of I. So if I give you a G1, to give you a G1 hat, to give you something else, I just have to add to G1 an element of I. And therefore, the probability that Z is contained in the vanishing of df dx1 less than or equal to the probability that Z is contained in the vanishing of G1. That's because once you fix a G1 so that Z is contained in this vanishing df dx1, then for any other G1, call it G1 hat, the difference is in I. And then for any other G1, you get an element of I. So you get an element, you get a polynomial, an element of I you can think of as a polynomial, so that Z is contained in the vanishing of this G1. Or in other words, the number of choices for G1 is at most the number of choices of an element in I, of the degree that we're looking at, degree tau in this case. Okay, but what is this probability here? Less than or equal to. Now, don't forget dimension of Z. Z was one of the irreducible components of this variety, and this variety was two-dimensional. So dimension of Z is equal to 2. And I'm now counting the probability that something two-dimensional is contained in a hypersurface. So a hypersurface to contain something two-dimensional. Again, you can use this degeneration argument that we talked about at the beginning. We did it for a curve that you degenerate into a union of lines, but something two-dimensional you can degenerate into a union of planes. And therefore, this probability is less than or equal to the probability that a given plane is contained in V of G1. We talked about whether that's it. Yes, the probability that a hypersurface contains a two-dimensional surface is less than or equal to the probability that the hypersurface contains a given plane, again by the degeneration argument. And when you compute this, it's very easy to compute that. You get q to the minus tau plus 2 choose 2. That's how you get the tau plus 2 choose 2. Okay, perfect. So now we have here probability that 2 holds. We have a lower bound. Let's go up to 1, 2, and 3. Okay, plenty of choices of G0. F0 is fixed. Remember, F0 is fixed. Plenty of choices G0 guarantee 1. Then once it's chosen, plenty of choices for G1 guarantee 2. And now we want to make sure that we arrange 3 as well. Fix G0 and G1. Fix F0, I should say first. Oops. Fix F0, G0, G1, such that 1 and 2 hold. And then we want to arrange 3 as well. Claim the probability that 3 holds. Probability, so here I should say as G2 is chosen in FQ x0 until x3 homogeneous of degree L is chosen uniformly at random greater than or equal to 1 minus L minus 1 square over Q to the top plus 2 choose 2. Or equivalently, probability that 3 fails less than or equal to L minus 1 square divided by Q to the top plus 2 choose 2. Okay, the proof, let's do the proof of this. What was 3? Remember, 3 is if I take C, so if C inside the vanishing of df dx0, df dx1 is an integral curve of degree d greater than or equal to L plus 1 over 2, then C is not contained in the vanishing of df dx1, dx2. This is what we want to accomplish. This is condition 3. This is condition 3. 3 says that for any integral curve, it's not contained in the vanishing of the next partial derivative. But look, how many such C's are there? This the sum of the degrees of all components, of all irreducible components, is less than or equal to L minus 1 square by Bézout's theorem. Therefore, there are at most L minus 1 square possible integral curves C. And in particular, at most that many integral curves C of large degree. And that's how we get the L minus 1 square. The L minus 1 square in the numerator is an upper bound for the total number of possible integral curves. Now we have to fix an integral curve contained in this vanishing. See, this vanishing locus, the one in the box in the middle of the screen, is one-dimensional. It can have a bunch of curves. It can split into a union of a bunch of curves. Now I have to fix one of them of large degree and prove that and give a bound on how often it can be that C is contained in the vanishing of the next partial. Okay, now fix C inside vanishing of df dx0, df dx1, integral curve, degree, large degree, L plus 1 over 2. We're going to use that it has large degree. And then probability that C is contained in the vanishing of df dx2, yes, which by the way is the probability that C is contained in the vanishing of df0 dx2 plus g2 to the pth power. Yes, that's how our partial derivatives work. This probability is less than or equal to, again, if g2 is so that C is contained in this vanishing and g2 hat is so that C is contained in the vanishing, then their difference must be in the ideal of C. So this probability is less than or equal to the probability that C is contained in V of G2 by exactly the same argument as before. If G2 and G2 hat satisfy this condition, there is this inclusion of C, then their difference must be in the ideal of C. So if you fix G2 and use it as a base point, you get an injection from the set of G2, which satisfy the inclusion C is contained in this vanishing locus, to the set of hypersurfaces containing C. But here C is an integral curve of large degree. Integral curve of degree, large degree, L plus 1 over 2. I have to bound the number of hypersurfaces that contain a given curve of large degree. How do we do it? You degenerate C. That's the argument we had before. This argument, the degeneration argument, we use it once again. Again, you degenerate C to a union of lines. Degenerate C. So this is less than or equal to, by the same argument we had before, union of D lines contained in V of G2. And this is very easy to calculate. This probability less than or equal to Q to the minus tau plus 2 choose 2. It's a coincidence that we get the same Q to the minus tau plus 2 choose 2. Okay, very good. So now look, we have upper bounds. We have lower bounds for the probabilities that 1, 2, and 3 take place. So many choices, you fix F0, many choices of G0 will guarantee 1. After it's chosen, many choices of G1 guarantee 2, many choices of G2 guarantee 3. So altogether, let's see, overall, the probability that E takes place is greater than or equal to 1 minus 1 over Q to the top plus 2 choose 2. This is choosing the first one. 1 minus L minus 1 over Q to the top plus 2 choose 2. This is to make sure the vanishing locus when you take two partial derivatives is one-dimensional. And then 1 minus L minus 1 square over Q to the top plus 2 choose 2. This is when you make sure that no integral curve contained in the vanishing of the two partial derivatives is contained in the vanishing of the third partial derivative. No integral curve of large degree. Now, it's a coincidence that you get the same tau plus 2 choose 2, but it's not a coincidence that you get something quadratic in both cases. Now, this is greater than or equal to 1 minus sum of all the numbers that we have in the three brackets. So L minus 1 to the I over Q to the tau plus 2 choose 2. I goes from 0 to 2. And this is greater than or equal to, and this is our goal, what we want, 1 minus 1 over Q to the A minus 1. Remember, this was the goal. I stated it before. That was the goal, that probability of E is greater than that. Provided that, this is true, provided that, well, this has to be for Q large enough. Yes, our goal was to prove that the probability that it takes place is greater than or equal to this thing in red for Q large enough. And that's the case, provided that, look here, I have Q to the tau plus 2 choose 2, and here I have Q to the A minus 1. Provided that tau plus 2 choose 2 greater than A minus 1. We're done. We're done. Because note, recall, A is 3L minus 2. That's the numerics. And tau of L was L minus 1 over P. So this is quadratic in L. And this is linear in L. So this holds for L sufficiently large, greater than or equal to L0, which depends on P, because tau of L is L minus 1 over P. The inequality for L that you have to solve depends on P. The larger the P, the worse your bound. But there we go. There we go. So, Antonio, do you have 2 minutes just to summarize?
Sure.
2 minutes. Okay, now to summarize, conclusion. Let K be FP bar. Write X as X1 union. Here I have this T2K union T and K, where N is L times L minus 1 to the 4th power. Then dimension of TD is less than dimension of X1. That's what we proved over FP bar. We did it with T check, but then from T hat, we can go to TD. By the way, one checks x1 is not contained in TD for d greater than or equal to 2. That's what you need in order to get from t check to TD, from TD check to TD. Okay, so all of these have smaller dimension. And now, what if you do the problem in characteristic 0? Let's go back to the original problem. If characteristic k is equal to 0, one can take L0 of 0, the bound for L, to be L0 of 2. Whatever bound, so I'm saying that if dimension TD over F2 bar is less than dimension of x1, then also dimension TD over maybe the complex numbers is also less than dimension of x1. Once you prove it in positive characteristic, it also follows in characteristic 0. I stop here. This is again an illustration of a moduli problem over an algebraically closed field that we reduce to point counting over finite fields. We were counting polynomials, and the point counting was a non-trivial point counting. We had to do the splitting of the partial derivatives, and then we used the language of probability. Once you have this red box here, the partial derivatives almost behave like independent variables, and then you just achieve 1, 2, and 3 one at a time.
Okay, thank you, Kaloyan.
Thank you.
I have a very quick question. So this invariance of dimension with respect to base extension and this upper semi-continuity, this is something that we learn in an introductory course in algebraic geometry. So it's a very nice illustration of this principle that you can reduce to.
Yes, notice that we used upper semi-continuity twice. You have a curve and then you specialize to union of lines. And then in spec Z, you have special points and the generic point, yes?
Yeah. So it seems to me that this method is effective if you deal with polynomials, with a single polynomial, with hypersurfaces. What happens, let's say, if you consider complete intersections? Can you, or the counting becomes very hard?
Aha, that's a good question. That's a very good question. Yes. The counting
because with these partial derivatives and like what you did here for hypersurfaces, I was thinking how would one could do that in if we have something of higher codimension. Yeah, so it gets more involved.
That's a good question, but I think it's possible to explore that. It may be worth trying it.
Okay.
Yes.
Any other questions?
Yeah. So, hi, I have a question. Oh. So, can you explain a bit about the dependence on the characteristic? It seems to me that it can be dropped somehow.
Yes. In fact, I believe that the whole statement will be now our proof. In our proof, there is dependence on the characteristic because here we have to solve this inequality that you see in red, and tau is L minus 1 divided by P.
Yeah, but if it are infinitely, if it's true somehow for infinitely many primes, that may be enough or something. Like if you prove something over characteristic 0, then it's true also for any P large enough. And you can detect it.
Yes. So what happens? Yes. So what happens in characteristic 2? What happens in characteristic 2? If I take P equals 2, I will get the best bound for L. So I get some bound for L, very explicit. That bound will also work in characteristic 0, and because it works in the generic point, you're right, yes, because it works in the generic point, the same will work for infinitely many primes. In fact, for all but finitely many, you just don't know for which ones you may have to do. You might have to take a larger L0. So you're right, for all but finitely many.
And then you can treat each one of the remaining cases individually, no? Can you do something like that?
Oh, but finitely. But you don't know which ones will be the exceptional ones.
Doesn't matter, like for which, right? So, I mean, can't you use it for any fixed FP bar, whatever?
For any FP bar.
Like you prove it for C, and then you get, and then you're left with finitely many FPs.
Finitely many possible exceptions, yes. So let's say maybe P equals 101. Maybe there the TD, the dimension of TD. Let's see. So you're saying that I can take the same L for all the primes.
I'm asking. It seems to me like
no, that's
could be some delicate argument that I'm missing, but it seems to me like it's somehow.
Yes. Let's see. Dimension of TD. So let's see what we know. Dimension, we know. Dimension of TD over the complex numbers is equal to dimension TD FP for all but finitely many P. And dimension of TDC is less than or equal to dimension TD over FP for every P. Here we use that TD is projective, and here we use just that the generic fiber has the same dimension as all the fibers for all points in some dense open. Yes. Dimension of this is less than dimension of x1. And we also know that the dimension of TD over F101 less than dimension of x1 only for L really large, yes? Maybe L less than 10,000.
But don't you have some kind of, doesn't your statement assume that L is large enough somehow? No?
Well, in my statement, let's go back. Let's go back to the original statement. Go back. The statement is that there exists a bound L0 which may depend on the characteristic, so that for all L greater than or equal to L0, x1 is the unique irreducible component of maximal dimension. Now, the question is, how does L0 really depend on the characteristic? Can it? By the way, I think that in the end, this statement will be true for all L. In the end, it's just the method proves it only for large L. Yes. In the end, it should be. But let's see if we actually prove that doesn't depend so much. Now let's see. Dimension of TD over F2 less. No, I don't find it obvious. Maybe so. Let's say dimension of TD over F2 less than dimension x1 for L greater than 20, maybe. Yes.
Yeah.
The question is, does this also hold? Does this also hold for L greater than 20? And I don't think the arguments would imply that.
No. But you can take. But both of them will hold for L larger than 1,000, 10,000. No. Like,
yes. Oh yeah, I can definitely take a uniform L. Yes. I can, if I want to, I can definitely take an L. Yes, if I want to. Yes. I know. I see what you're saying. Yes. Okay. So dimension of TDC is dimension of TDFP for all but finitely many P.
So there
can be some exceptions. There are finitely many exceptions. I can take the largest L that works for the exceptions and the one that works for the generic fiber, and then any L greater than that works uniformly for all the primes. Yes. If that's
Yeah.
what you're saying. Yes, I agree with this, but I prefer to state the theorem the way it's stated, because if I'm interested in the L for the characteristic 0 case, I'm better off taking the L in characteristic 2 because it's smallest.
Okay.
Yes, you're right. I don't have to state it like that. Yes, I agree. There exists an L0. Absolutely, yes, such that for all L grade, I can say it this way. Yes. The reason I state it this way is that I emphasize if the characteristic is small, we can give a better bound for L0. But you're right. Yes, I agree with you. Yes.
Okay. Any other questions? If not, let's thank Kaloyan again, and we'll meet again next Monday from 3 to 4.
Thank you very much. Thank you.
Very cool talk, and